So let's talk about how to derive trig functions. Now, the trig functions that I'm referring to are sine, cos, and tan for the moment.
Yeah.
Now, you are aware already, because you've already learned this at school, that the derivative of sine x is equal to cos x. And this is what we're going to be focusing on. And we're really going to be sort of focusing on sort of the why this is true, okay? So this is correct, but we want to figure out why. Now, to do that, we need to sort of establish a sort of few other sort of concepts. So I want you to draw to scale for me, if possible, y equals sine x and y equals tan x on the same axes. And it's important that I want you to draw them both on the same, on the same axes. And I don't need you to draw the entire graph. I just need to draw up to, from, let's say, from 0 to pi over 2. So, you're going to be kind of drawing perhaps with a mouse and, so I'm not going to nitpick on, like whether the curve is absolutely perfect or anything like that. But I am clearly looking for something particular here. And I want to see if you understand something. So, draw it out. And, if it's because of the mouse that you can't draw it perfectly, you can tell me. But, I am looking for something obviously here. I want to see what your understanding is of the graph of sine x and tan x from 0 to pi over 2. So I'll give you a moment to do that. So now that you've drawn this sine and this tan, and you've got your vertical asymptote pi over 2 and so on, like my question is, apart from imperfections due to drawing with a mouse and all that kind of thing, and I don't care about that, do you think this graph accurately represents what you would see if you draw y equals sine x and y equals tan x on the same axes to scale? Is there anything like, if you think it's accurate, then say it's accurate. If you think it's not accurate, then what would you change? Like if you were able to, So, I'm also not going to really care about the fact that, okay, you're saying this is 1, right? You're trying to tell me this is 1 and this is pi over 2, right?
Yeah.
Well, pi over 2 is 1.57. So obviously this is meant to be longer than that, which it clearly isn't. But again, I'm not going to nitpick over little details like that, all right? You can scale it, you can, select it, change it a bit. Not worried about that. So my question is, are you happy with this graph? And you can say yes if you are. I mean, I'm just, I need to know.
Yes.
Okay. So then I want to ask you, between 0 and pi over 2 inclusive, or let's say exclusive, right? How many points of intersection are between y equals sine x and y equals tan x?
I think it's probably just one intersection.
All right. So you're expecting, are you including 0 or not including 0?
Oh, like 2.
Okay. So to be clear, when you say one intersection, you mean this one, yeah?
Yeah.
So basically you're saying that, if we don't include 0, so if we do not inclusive, then, you're saying there's one acute angle such that sine x equals tan x. That's what you believe, right?
Yes.
And you kind of would expect that because, sine x kind of looks like this curve and tan x does this curve. And so, and tan x goes to infinity and, and it's concave up and sine x is kind of concave down. So you expect that they'll meet somewhere, yes?
Yeah.
So if you believe that there is a point of intersection, then can you find that point of intersection for me? So for acute x, let sine x, equals tan x and solve. All right. So you've done trig equations before, so you should be able to do this. Can you solve for that and tell me what your answer is?
Yes.
So you appear to have come up with a answer that there is no point of intersection. So how did you solve it? How did you approach it?
Yeah, so it's sin x equals sin x over cosine x.
Okay. And then how did you solve that?
And so it's 1 equals to 1 over cosine x.
Oh, you divided by sine is what you did?
Yeah.
So, okay, so you're saying 1 equals 1 over cosine x, and then?
So cosine x equals
So you're saying only x equals 0?
and pi.
Oh, well, yeah, for 0, yeah, obviously, and well, not pi, actually, and 2 pi, and so on, and so on, and so on. So not pi, because it's -1 then.
Yeah.
But, I'm focusing on answers from 0 to, pi over 2. So that's how you solved it?
Yes.
Is there any comment you want to make on how you solved it?
Um.
On the how you solved it. So not worry about the answers yet. You want to comment on, have you found all the answers to this question yet? Or have you thoroughly found all the answers yet?
No,
Why not?
because you asked this question.
That's not a valid reason. It might be a hint, but it's not a valid reason.
Oh, because we need to consider the range. Like
No, how did you solve it? What did you do here?
just eliminate sin x.
By? What did you do? You divided by sin x, right?
Oh yeah, right.
Whatever you assumed if you divide by sin x.
Oh, so wait, it cannot be 0.
So you assume sin x is not equal to 0. Does that make sense?
Right.
Now, which means if you do it your way, you've kind of made an assumption that sin x is not equal to 0, but can sin x equal 0?
Yes.
All right. Now, I don't think it will make a difference for this question, but I'm talking about your technique here. So if you consider sin x equal to 0, well, x equals 0 is true, so therefore it is a solution. But that doesn't really change anything because we already know x equals 0. But what matters is the fact that you eliminated a solution, even though it just happened to be here anyway.
Yeah.
Okay, so be careful with that. So if you're doing it that way, you need to sort of consider when sin x equals 0. So I probably wouldn't do it that way. I would very rarely would I recommend you, you have to worry about this. So I would recommend instead, I mean, it's not that different, but, and this doesn't just apply to trig, it applies to all your sort of equations.
Yeah.
I would recommend we do sin x equals tan x. And yes, I would make that equal sin x over cos x. Now, what I won't do is I won't divide by sin x. What I'll do is I'll multiply by cosine x. And then I'll move everything to one side. And then factorize. Does that make sense?
Yeah. It's
So we haven't divided. We haven't made any assumptions, which then allows me to make the conclusion that for this to be true, sin x equals 0 or cos x minus 1 equals 0 or cos x equals 1. And then, of course, I get my answers there. So that's 0, pi, 2 pi, etc. And negative as well if I care. And, x must equal 0, 2 pi, 4 pi, and, also the negative ones if I care. But, for x from 0 to pi over 2 for acute, that means x equals 0 only. And there is no solution for, x strictly between pi over 2 and 0. So there's no solution for x acute.
yeah.
Now, so you didn't get the wrong answer, but I was just more focusing more on the sort of dotting your I's and crossing your T's here. doing it your way, if this was an answer, you would have missed it out.
Yep.
Like if it was an answer and it wasn't here, yeah.
Yep.
So again, you know, you're trying to make sure that you don't make careless mistakes. And so that means it's good practice to really never divide, or if you divide, explicitly consider what if that equals 0.
Yeah.
And because lots of students may forget to do that, then it might be better practice just to avoid dividing in the first place, because, you know, then it just means you can factor it out. And then it's very clear that it could equal 0.
Yeah.
All right. But at the conclusion of that, what do we conclude?
So there is only one intersection.
Exactly. So we therefore conclude there is no point of intersection between y equals sine x and y equals tan x for x acute. I mean, clearly there's one at x equals 0, but for x acute, there is no point of intersection. And so now, given that information that we've just done, how can that possibly be the case? Can you try to draw it again? Like, does this make sense? Like, how can that happen? Like, you know what sin x looks like, you know what tan x looks like on separate graphs. So you think and thought that there was a point of intersection, but now we know there isn't. So again, can you draw sin x and tan x on the same graph to scale-ish, you know, focusing on certain aspects, in this case being there's no point of intersection. So what would it look like then? So I'll give you a little while to think about it, but you know, this is the point I want you to think about.
Right? Or it's...
Well, yeah. I mean, so you know, you sound very stumped and you feel like you can't possibly expect anything except this. Well, I can tell you that if you draw this on separate graphs, I would say you're okay, right?
Yeah.
So I'm not saying your graphs are wrong. I mean, obviously there's little details we could fix, but I think that's more because of the mouse. So obviously you can't have this turning back a bit, right? And obviously this is not to scale and blah, 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 but there's all tiny details that are mostly due to the fact of drawing with the mouse and, you know, don't care about that here, right? And so, yeah, your sine graph is right, your tan graph is right, but I'm asking you to draw them on the same graph. And now this is wrong. Because, you know, obviously you can't have a point of intersection. And I'm asking you, can you now draw them on the same graph? And now that you understand there's no point of intersection, can you see how it would work?
Oh, maybe we can just add a circle like between the intersection.
So you're saying, well, let's cheat. Let's say that somehow sine x and tan x just don't have a value when it's acute.
Yeah.
Well, you know that's clearly not true, right? I mean, tan x is defined for all acute angles, and sine x is defined for all x. So you know that's not true.
Yeah, so how can we draw that?
Okay, so, and this is exactly why I'm trying to get you to think about it, because many students, including yourself, you know, think it looks like this, right?
Yeah.
But it doesn't. At least, you know, I mean, separately they do, but together they don't, right?
Yeah.
And, you know, the answer is that they have no point of intersection. We've already worked out, we've already proven that. And so the next thing is, okay, well, can you draw that? And, you know, some students might be able to then figure out what's going on. And in your case, you're saying you're still a bit stumped. So let me show you. So as I mentioned before, it is correct to draw that separately. But when you're drawing them on the same graph and paying attention to details and scale, what I'm trying to tell you is that sine x is concave down, but when you pay attention to the scale, it's like this. I'm exaggerating a bit, but not that much. This is 1 and this is pi over 2, right?
Yeah.
So, you know, like, you know, 1 and 1.57, so kind of to scale, roughly. And tan x is concave up, but it basically goes like this. it like basically it was always above.
Yeah. Yeah.
Like, you know, does that make sense?
Yeah.
So this is y equals tan x, and this is y equals sine x. And, you know, you can probably see that it's, you know, if we look at certain points, it might make sense. So you understand that this is 1 pi over 2, right?
Yes.
Pi over 2, 1, I should say. And this point in white is, you know, this is line y equals x. And you can see this is the point 1, 1, right?
Yeah.
And this, if you're looking at when tan x equals 1, this is the point pi over 4, 1. So, you know, pi over 4 is, you know, less than 1, right?
Yeah.
So it's about 0.78 or so, roughly. So you can see that 0.78, tan's already hit 1. Then at 1, y equals x hits 1. Then at pi over 2, you know, which is like 1.57 or so, it hits 1. So can you see that it makes sense that tan is the most steepest, then the y equals x, and then y equals sine x?
Yeah. That makes sense.
So it is, and you do have this graph, and the you know, and the shapes are correct. But when you draw them on the same axes, then you need to pay attention to the fact that they do not cross.
Yeah.
In the acute domain. And I mean, they obviously cross at 0, but they do not cross there.
Yeah.
Now, let me show you that. I mean, I'm sure you've got a graphics calculator, which we'll be able to show you, but let me show you on the screen as before. So let's look at our graphs here. We've got the red one being y equals sine x, and, you know, we're zoomed out for the moment. And you've got the blue line being y equals tan x, right? So this y equals sine x.
Yeah.
You got y equals tan x, which kind of looks like that with, you know, its asymptote there at x equals pi over 2. And so, you know, drawing them separately, of course, they do look, you know, like that. But drawing them together, you can see it looks like that. And we'll put in the line y equals x, and you'll see why in a moment. And let's now zoom in. And from 0 to pi over 2, you can see that sine x is always below this green line, which is y equals x. Tan x is always above. You can see that, you know, this is pi over 4 here. This is, you know, 1, 1. And this is, you know, pi over 2, 1. And so this is drawn, you know, sort of to scale here. Yeah.
That makes sense.
Now, so when we say that this is x, let's be clear. What unit is x in? So when we say sine x and tan x and y equals x, what unit is x?
The unit, so it's pi.
Oh, pi is not a unit. So how are we measuring the angle? Like, what unit is it?
Degree, other radian.
Yeah, so this is radian. So to be perfectly clear, when we're drawing it, this is in terms of radian, not degrees, and that's important, all right?
Yeah.
And the results we're about to say are all about in radian. So this is in radian. So now what do you think happens? So ignore tan for the moment, ignore tan. Let's ignore tan for the moment. Let's look at sine. Now, when you get really small, when you get smaller and smaller, what do you think happens to sine x, which is red, and x? What can you tell me about their values?
The value. So it's pretty close.
Yeah. What about tan x and x as x gets smaller?
X is getting far away.
Wait, as x gets smaller, what about tan x and x as x gets smaller?
Yeah. Right.
The
So
values are getting
close.
closer. Again, not far away, closer, right? Now, will tan x ever be smaller than x when it's a cube?
Nope.
Will sine x ever be bigger than, you know, x when it's a cubed?
No.
No. And so they will always be smaller. So what we have is this fine, you know, we can zoom in a bit more, but no matter how far we zoom in, you'll find that, you know, we're going to zoom in a lot. But, you know, like, I mean, you can see we're quite zoomed in, but you basically can't tell the difference between 3 lines right now, right?
Right.
If we zoom out a bit more to sort of, you know, okay, you can start to see they start splitting up a little, right? And, you know, blue is still on top, then green, then red. So it's still tan and sine x and x, right? But we're reasonably zoomed in already, yeah?
Yeah.
Like, you know, if we zoom in, but, you know, the smaller we get, you can see that they just get closer and closer and closer. And, you know, then again, you almost can't tell the difference again, right?
Yeah.
So therefore, the important results that we're going to get out of this, and let me zoom out. So what we are saying, and I'm going to write this on the left-hand side where it's sort of thing, but you can hopefully quite see this quite clearly from our graph. For x small and in radian. So remember, this is in radian, right? For x small and in radian, sine x is approximately equal to x is approximately equal to tan x. And the smaller you go, the better the approximation, right?
Yep.
Now, we also say that for x acute, then without exception for x acute, you know, sine x is strictly smaller than x, which is strictly smaller than tan x. So they might be around equal, they could be approximately equal, but technically sine x is always smaller than x, which is always smaller than tan x, all right?
Yeah.
Now, you happy with that?
Yes.
Good. So given what we've just said, we've now basically just said that for x in radian, and that's important, obviously it doesn't work if it's degrees. If x is in radian, then for x small, sine x is approximately equal to x. And, you know, it's also approximately equal to tan x. And, you know, we also said that it's actually not equal, but, you know, and tan is always bigger than x, is always bigger than sine. But for now, let's focus on the fact they're approximately equal.
Yep.
So what do you think is the limit as x approaches 0 of sine x over x?
The limit. So it's 1.
Yeah, because they're roughly equal the smaller you go. So if you go basically as small as, well, basically 0, but not reach 0, then yeah, the answer will just be, well, 1. And the limit as x approaches 0, obviously of x over sine x being the reciprocal would also be equal to 1, right?
Yes.
And the limit as x approaches 0 of tan x over x will be
1.
And the limit as x approaches 0 of x over tan x will also be
1.
Right. Good. So these are some important results that you may be tested on. And we've kind of just showed you why this is true. Now, it's important to recognize that this is, you know, I mean, I've said it a few times, but this is for radian, right?
Yeah.
So this is one of the things that will help us figure out what the derivative of sine is. This is like the part 1, right? If you haven't done this, then we kind of need this, all right? Yeah?
Yeah.
So what is part 2? Well, remember our aim was to work out the derivative of sine x equaling cos x, and we wanted to show this. And right now, we have one of the tools available, which is the limit as x approaches 0 of, you know, sine x over x equaling 1. Now, the question is, this is obviously not related to the derivative directly itself. So the next question we need to ask is, how do we find the derivative of sine when we don't know its cosine?
I have no idea.
So the question you need to think about is, how do you find the derivative of anything?